Okay, everybody, welcome back here to another quick chemistry video. This is actually part 2 of that quick video about orbitals, electron configuration. Here we're going to focus mainly on just electron configuration in this one. So if you remember from the first video, if you did not watch it, I'll maybe put a little link somewhere up here where you can go watch it. But we have orbitals that hold electrons, and there are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. Now each of these orbitals and subshells, s being an orbital, p, d, and f being subshells, as there are more than one orbital that makes them up. There is just one type of s orbital. There are 3 different types of p orbitals, which makes it a subshell or sub-level, depending on your book or who's talking. D, there are 5 different orbitals, which also makes it a subshell or sub-level. And F, there are 7 different orbitals, making the F also a subshell or sub-level. Remember, each individual orbital could hold a maximum of 2 electrons only. So that means maxing out our orbitals are our subshells here. For our S, it is going to be 2 maximum electrons. For our P subshell, 6. For our D subshell, 10. And lucky number F there. I guess it's a letter, not really a number. F, it could hold 14 electrons here. So that's really important numbers when you're writing electron configuration. If you know that, and you know what we talked about in the previous video there, that on the first energy level, the n equals 1, which is the principal quantum number 1, ground state, closest to the nucleus, you just have s orbitals. That's where they begin. It's not until you get to the second energy level that you start to see p orbitals. Not to get to the third energy level that you see d orbitals. Not till the 4th energy level there you see the f orbitals start to appear. So why is that important? Well, that's important because if you know this and you know this, you can then put together the correct order at which electrons go into the atom, and you can write any electron configuration you want. How do you get to that correct order? Well, you can make your own chart. And basically, you start with our 1, 2, 3, and 4 we just talked about. And what I mean by that is first energy level, there's S's. Second energy level, that's P. So go down a little bit to the right and put 2P. Third energy level, D, down a little bit to the right, put D, 3D. And down a little bit to the right, 4th energy level, that's our F's. Once you have that kind of 1, 2, 3, 4, all you got to do, fill in the numbers underneath each of them. I put a 2s there, a 3s there, a 3, sorry, if I could count right there, 4s, a 5s, a 6s, and a 7s. Remember, it goes about 7 energy levels. Under the P, just do the same thing. 3p, 4p, 5p, 6p, 7p. For our D's, 3D, 4D, 5D, 6D. And for our F's, 4F and 5F there. Now, let me just grab an eraser there, kind of fix my bad counting. It happens. It's live. What are you going to do? That's going to be a 4S there. That looks a little bit better. Now, you may be saying to yourself, what about like 7D, 6F? You really can't get there on anybody on the periodic table. And honestly, even if you wrote those numbers, like down in this area where we have 6D, then you might want to put 7D or 6F. You'll never use them on anybody on the periodic table. So not a big deal if you kind of put too many numbers down in this region. It'll still be okay. But you'll never use them pretty much. So how does this work? Well, we always start up here and we basically just follow the arrow. So we go down to there. Once that's full, we come back and zigzag back Once that's full, we come here. Once that's full, we come here to 3p. Remember 3p, then it's actually the 4s, then back to the 3d. And again, that pattern continues. We see our 5s, back to our 4d, and we continue this pattern. I won't draw all the arrows in there, but you just keep zigzagging back, and that should get you the correct orders that you need. So how do we use this? Well, we use this that we just created. We use the fact that we just talked about S's could hold maximum of 2 electrons, P subshell 6 electrons, D subshell 10 electrons, and F subshell 14 electrons. Now again, you could pretty much write any electron configuration you need. So let's just take one, for example. Let's take our friend nitrogen. Nitrogen is, if you look on the periodic table there, number 7, and that means it has 7 protons. And if this is neutral nitrogen, it would also have, to balance it out, 7 electrons. And that is what we need to fill. So we will start here. We always start here. We will come down. First spot we hit is 1s. So electron configuration 1s2 up on top. We then would need to come back around to here. And now we're going to hit 2s2. Now, if you're not sure what each of these numbers means, a quick once over on what each of these numbers mean. First number here is actually the N number, or the principal quantum number. So that is your energy level, basically, or your principal quantum number. This is the orbital, or subshell, that the electrons are in. And the number up on top is actually the number of electrons in that subshell, or in that orbital. So we're not done actually with our electron configuration. We just count the top numbers. S2 and 2 is 4. We actually still need to continue. So we're going to continue this way. We're going to zigzag back. Now we're going to come to our 2p. And here we would go 2p. Remember, the p subshell could hold 6. We've already placed 4. That means we have 3 more to go there. And that would give us our electron configuration 1s2, 2s2, 2p3. That's the way you say it. That's also the way you write it without the circles. So again, it would be 1s2, 2s2, 2p3. No commas, no dashes, which is what people for some reason like to do a lot when they're kind of writing electron configuration. Now, if we look at something like calcium, again, if we look on the periodic table, let me draw my really wonderful looking periodic table here. Got a number 20 up on top. So again, that's the atomic number, meaning it's got 20 protons and 20 electrons to balance it out, to give it no charge and neutral. So again, we would start up here at our top. It would drop a different color so we could kind of see it maybe a little bit. Let me go that way. So again, we're going to start here. So we're going to go to our 1s2. We need to continue on, zigzag back. Now we're coming to our 2s2. Coming here, zigzagging back. Now we could go to our 2p. Remember, it could hold 6. If you've lost track, you can just count the top. 2, 4, and 6 is 10 electrons at this point. We actually have 10 more to go, so we got to continue down. Next is the 3s, as you can see there, and that could hold 2. We need more, so we're going to zigzag back. Now to our 3p. That subshell could hold 6. Once again, if we count the top numbers, 2, 4, and 6 is 10. 2 more is 12, and 6 more is 18. We're almost there. Remember, the beauty of this chart takes you in the right place next. Not the 3D after the 3P. It's actually the 4S. And that would take us to 4S2. That's giving us 20 for our total electron configuration at this point. So if you follow this chart, you pretty much will always get the right electron configuration. There are a couple of exceptions. There's actually a number of exceptions. Two exceptions, for example, would be chromium, number 24, and copper, number 29 on the periodic table. And if we were to write our electron configuration like we normally would write it, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, 3d comes next. Again, if we were coming here, 3d actually comes next. And that would be chromium's configuration if you follow that chart. Actually, this is where the exception occurs. There's actually one more electron up in the d orbital, one less electron in the s orbital, and the correct configuration for chromium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So you can see here, that is the exception, been found to be more stable with one extra electron up there in the d orbital, one less electron in the s. Now, copper is the same deal, except it has 29. So copper will look pretty much identical to this, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Again, an extra electron up in the d, one less electron up there in the s orbital. And again, this would be the electron configuration for copper. Now, a couple other things here as we're talking about electron configuration, and that is a shortcut to the configuration. So for example, if we take, and we grab the right thing here, what am I looking for? Maybe that will work. If we just highlight calcium's configuration up to this point, put a little highlighter on it there, and we just count up how many electrons are present at that point, and we count up the top number, we will see that we have, again, let me get the right color in there, try that color. We got 2, 4, 10, 12, and 18. If we look at the periodic table, number 18 is argon. So we actually can shorthand this configuration by putting brackets around argon. And what that implies is what I highlighted here, argon's configuration. And then we could just continue on with the rest to get to calcium. And what goes in this bracket always is the noble gas that comes right before whatever you're writing the electron configuration for. So for example, if we took chromium over here and we highlighted chromium, maybe with this color would be good. We went from all the way to here, and even we did actually copper underneath it as well. We'll highlight here, as they're both the same. And if we count up for each of those, chromium and copper, how many electrons I just highlighted, 2, 4, 10, 12, and 18. And again, 2, 4, 10, 12, and 18. Those also are argon. So we could shorthand chromium by saying argon, continuing on with its electron configuration, 4s1, 3d5 in this case. And for copper, again, argon, 4s1, 3d10. Now you may be thinking, is it always argon? And it's not. It's always the noble gas that comes before whatever you're writing electron configuration for. So for example, if we look at sodium, which is 11 electrons, again, following our chart, 1s2, 2s2, 2p6, 3s1 in that case. Once again, if we look at the electron configuration up to here, that is 2, 4, and 10. on the periodic table, it is neon. That is number 10. You could shorthand this by neon in brackets 3s1. So that's sort of a shorthand. Some people call it maybe sometimes a noble gas configuration. Again, got to be a noble gas that kind of goes in that bracket. One last thing here to wrap up this quick video before we end it on electron configuration is ions. So ions are things with charges. There are cations, which are positively charged, and that's a result of losing electrons. There are anions, which are negatively charged, a result of gaining electrons. And how does that affect electron configuration? Well, when we look at, say, sodium, since we have it up here, sodium is group 1, makes a +1 charge, which means it has lost 1 electron from its neutral state, which means it actually will have only 10 electrons. By the way, in case you're not sure how you get that, sodium still must have 11 protons. Otherwise, it's no longer sodium. And it would need, as you can see there, 10 electrons, 11 positives and 10 negatives, leaves you that +1 charge left over that we see in the sodium ion. The configuration for the sodium ion would be 1s2, 2s2, 2p6. Again, as we've seen, that is neon's configuration. Now, what happens if you have something with a negative charge? Let's take oxygen. Neutral oxygen will have 8 electrons. Configuration 1s2, 2s2, 2p4 in this case. Oxygen, when it creates a charge, makes a -2 charge, an anion, which means it has gained 2 electrons, and actually will end up with, believe it or not, 10 electrons as well. Again, how you get there, because it's still oxygen, it has 8 protons, which are positively charged. And to have that overall -2 charge, it has 10 electrons. 10 negatives plus 8 positives leaves you that -2 left over, again, where the charge comes from. Well, you probably guessed it by just looking. 1s2, 2s2, 2p6 is the configuration for that. Our neon's configuration. That means that when representative elements, not transition metals, but ones outside the transition metals, metals and non-metals, they actually end up in the noble gas configuration when they lose or gain electrons. That's really, as you'll probably learn if you're doing chemistry, the purpose of bonding is for everybody to achieve that stable noble gas configuration. They don't become the noble gas elements, but they become just like them in terms of their electrons, which makes them really, really stable. And that is what is known as being isoelectronic. So the sodium ion, neon, and the oxide ion are all isoelectronic with each other. They all have the same electron configuration. One last quick move on electron configuration. Transition metals are a little bit different when they make ions. So transition metals, when they make ions, actually a little bit different because they involve the d orbitals. So for example, what happens when electrons go into our transition metals, as we saw from our chart, they do fill the s first because it's lower in energy. Then they go in and fill up whatever in the d orbitals they need, energy increasing. What happens though once they start filling those d orbitals is there's actually a switch in energy that occurs, and it ends up being the 4s in this case orbital, so actually ends up being higher in energy than the 3d after they start filling. And that's really important when transition metals lose electrons, because things typically lose the highest energy electrons, which means now that they have those electrons in a d, they're actually going to lose the s's first and then the d's if necessary. So a quick example of that, iron, lucky number, dead center of the periodic table, 26 electrons. I'm going to shorthand it here. I'm going to do a little argon, 4s2, 3d 6. And what will happen, for example, if I had iron with a +2 charge? Means it has lost 2 electrons, so now it has 24 electrons. It will actually lose, for example, let me actually just make this like, I think I did actually, 1, 2, 3, 4, 5, and 6, perfect. We'll actually lose these electrons first, and the configuration here for iron with a +2 charge will be argon 3d6. Now, what happens if iron actually had a +3 charge? Well, it would actually then have 23 electrons. What's going to happen in that case? Well, it is still going to get rid of these guys first, but that's only 2 electrons. Then it needs to actually go into the d orbitals and get rid of an electron, giving us argon 3d5, as it then will take an electron out of there. The transition metal is a little bit different. They don't end up at noble gases when they lose electrons, but they always lose the S's first and then the D's. I know I said that was probably going to be it, but one last thing popped in my head, and it gives me an excuse to draw a really bad looking periodic table, which is always a good thing, I think. So if we look at the periodic table, 1, 2, and we'll do 3, 4, 5, 6, 7, and 8. Super badly drawn periodic table. Here we go. Sort of like a periodic table if we close your eyes. All right. So when we look at the periodic table, we have our period. So we have period, and I'll just kind of do, we have really 7 periods. 1, 2, 3, 4, 5, 6, 7. And when we have those 7 periods, and usually up on 1 here, period 1 is hydrogen, and helium over here in group 8. It's usually on most periodic tables. And truth be told, we're about, I would say maybe right about there. I'm gonna try to erase it and make it look a little better here. I'll probably take out my entire periodic table, I figured. Let's see if we can put it back together. And we'll do a little bit of that. We'll come on down this way. I think my table's getting even worsely drawn here. There we go. Semi like a periodic table there. So again, period 1 kind of goes with hydrogen, and then we have 2, we have 3, and then we have 4 kind of going this way. Now, group 1 and 2 on the periodic table is your S block, right? And they can hold 2 electrons, so that's 1 and 2. Groups 3 through 8 is your P block on the periodic table. And it could hold 6, 1, 2, 3, 4, 5, and 6. The transition metal region here that I try to get in here is your D block, and they could hold obviously 10. If you count the boxes in the transition metal all the way across, you'll have 10 boxes, and the 2 rows on the bottom of the periodic table there. That is your F block. And you can sort of count off on the periodic table electron configuration by simply just counting the boxes, basically. You know, if you went from period 1 here, that would be like 1s2 to helium. You come on to the next period there, that's going to be 2s2 to beryllium. If you cross over, you go across, that's going to be 2p6 all the way down to neon. And so forth. You come to the next one, 3s2 to magnesium, 3p6 if you go across to argon. Remember, this is now 4s2 here to our calcium. And this is where I wanted to kind of stop. Now that is period 4, and this is our first transition metal, SC. And that though is 3D. Remember, the D start in the third, and they are 1 behind the period number. And down here in the F block, that is 4F and 5F, which technically these guys kind of go in here on the 6 period, and they are actually 2 behind. So it does get a little bit crazy in there if you're trying to count on the periodic table. Electron configuration, especially if you're in a transition metal region, are kind of below. But on the outside ones, you can just literally count the boxes. So for example, again, our sodium that we did would be somewhere in this ballpark, right about there. Again, you would go, if you were counting, 1s2 to helium, 2s2 to beryllium, 2p6 to neon, and then right here 3s1 to sodium. So you can literally count it off. You could actually even do the transition metals if you're careful. Again, we would go with a different color here. We'll try purple. 1s2 all the way across to helium, 2s2 to beryllium, 2p6 to neon, 3s2 to magnesium, 3p6 to argon, 4s2 to calcium, and then you could actually count boxes: 3d1, 3d2, 3d3, 3d4, 3d5, and 3d6. Right there would be our friend iron. So you could count off electron configuration from the periodic table if you like, or you could do the chart. The chart probably will always get you the right answer. You might miscount on the periodic table, but you definitely could do that. All right, well, I hope this helped. I hope this will help you with electron configuration. Again, if there's any topics you want me to kind of cover quickly, let me know down in the comments. Thanks for watching, and I guess we'll see you on the next